So the next part of the geometric distribution that we need to think about is that of the mean and the variance. Now, hopefully it feels somewhat intuitive that if something has a 1 in 8 chance of happening, so there's a success in 1 in 8, then you would expect to take about 8 attempts to get that one success. Again, if it's 1 in 12 as a probability of success, then you would expect around about 12 attempts before you got that success. So hopefully from there we can see that our expected value is linked incredibly strongly to our probability and is indeed 1 over p. Our variance is 1 minus p over p squared, and we can look into that formula in a little bit more detail later on in the course. But we can prove that expected value formula from the stuff we already know about expected value. So we know that the expected value is the sum of each individual value multiplied to its probability. So in the case of the geometric distribution, we know it starts at 1. So what happens if you succeed on the first attempt? Well, that's just the probability of success. If you succeed on the second attempt, you've had 1 fail and 1 success, and we are multiplying that by how many times have we had to go, so that's 2. The next one, we would have failed twice and succeeded once, and we've got 3 of those. Again, it's that multiplying by x here that I've got, and so on and so forth. In order to manipulate this a little bit, I'm going to write this out in a slightly different way. So I am going to start off with one line of working. It's going to have p and then one of the p 1 minus p's in it. And so I know that I've got a second one here to make up the 2 in my original sum. And then the third term, I've got p 1 minus p squared, but I've got it 3 times. So I'm going to stack them. And what I'm doing here is creating like a set of infinite sums that I can manipulate each in turn. And if I add up the total of all of those, it's going to go back to the original line. So the next one would be p 1 minus p cubed, and again, and again, and one more time. We're carrying on. It's an infinite sum, so we'd keep going forever. So that means I can use the sum to infinity for a geometric series for each one of those. So if we have a look at this one, this is a over 1 minus r for that formula, don't forget. A is p, and our r term is 1 minus p. So I've got 1 minus p, which is just p over p, which is 1. The second one, I've got the same r value, so that's just p on the bottom, 1 minus p. But my first term is p 1 minus p. So that's leaving me with 1 minus p as my second term here. The third one, my a is p 1 minus p squared over that same denominator I've had several times now, so 1 minus p squared. And so on and so forth. So as I've done this kind of set of smaller sums, and I've got an infinite number of those, as I add up each one of those rows, I've kind of created another geometric summation here, because I still need to add all these up to get back to the original total. So in this case, this new sequence that I've got running down the right-hand side here starts at 1. Our geometric common relationship is 1 minus p. And so my sum to infinity in this case is 1 over 1 minus p, which is the 1 minus p I was interested in. So you can see that actually using what we know about an expected value anyway, and the fact that we're in a geometric distribution, so geometric series is probably going to be fairly handy, we've actually managed to prove it using our standard results that we know right now. Both of these formulas are in the formula book. We just need to know how to use them as well. So let's have a look at an example then. So Simeon's a tailor. He records the numbers of faults per metre of cloth, and he finds there are, on average, 8 faults per metre. Now that feels like a Poisson distribution to me, and somewhat unsurprisingly, part A says, state, giving any assumptions you make, a suitable probability distribution for x. Now x is already defined, so we don't need to worry about that. But I would say that it is a Poisson. And the reason I would say it's a Poisson is because we can assume that the faults occur singularly, that they are independent. Although you might disagree, but we could assume that. And we could assume a constant average rate, which are the conditions you need for a Poisson distribution. So as long as they're in context, scribbling that down for part A is what we'd want to be doing. Part B then says, find the probability that in a randomly chosen metre of cloth there are more than 2 faults. So for part B, don't forget that writing a probability statement is part of your working. You can't miss that bit out. That interprets the question correctly for you. And then we tend to go less than to calculate probability. And that's 0.0474 using the calculator. Part C then, the preamble says Simeon cuts the cloth into 1 metre lengths. Okay, so now we've got a set of independent metre lengths. Find the probability that the first time he encounters a metre of cloth with more than 2 faults is in the 7th metre. We've got that first time idea that tells me I'm in the geometric distribution, and I need a probability. But I have that because I've worked out the probability of more than 2 faults in any given metre of cloth already. That was part B. So I've got what I need, a mention of a first time in a number of trials and a probability of success. I'm in a geometric here. So I've defined a new variable. Y is the metres of cloth before the first time, there's that key kind of first time, more than 2 faults are found. So Y is following a geometric distribution. Probability of success is the 0.0474 we found previously. So we want that to happen on the 7th metre. So Y is equal to 7. Well, that means we've failed 6 times and then succeeded once. That is 0.0354. Part D says, find the expectation or the expected value and variance of the number of metres of cloth he cuts before he finds a metre with this fault, this particular fault, so no more than 2 faults, sorry. So our expected value then is 1 over our probability, which sorts itself out to being 21 metres before he finds that, or it's the expected number of metres he'd have to cut before he finds that condition. And how much does that vary by? So we plug that into the formula. So 1 minus p over p squared, which comes out at a massive 44. And you'll probably find that variance is fairly high on these sorts of things. Tiny, tiny probability, fairly large variance, as I'm sure you can see. Right, part E says if a metre of cloth containing 2 or more faults occurs before he has cut 3 1-length metres, he sends a roll of fabric back. So here he is, he's just gotten a new roll of fabric, he unrolls it and he starts cutting these fabric metres up. If he finds these bolts of cloth with more than 2 faults in them before he's really gotten anywhere into that roll, so before the first 3 metres, he's going, look, this particular bolt that you've sent me is rubbish. Take it back. We want to find the probability that he sends back 2 consecutive rolls of cloth. And so I'd always advise with these sorts of questions to take them really carefully and think through the kind of actual logic behind the question. So rather than jumping in and assuming you're going to be able to do this in a line or 2, I think very carefully about working your way through the probabilities. So notice that it has changed. If a metre of cloth containing 2 or more faults, so we have actually changed that slightly. Therefore, we need a new probability. We could probably find that first. So probability of more than 2 faults we worked out previously. This time we want 2 or more. So x greater than or equal to 2. It's the same as 1 minus the probability that x is less than or equal to 1, which is 0.1912. Okay, so I've now found a better probability for this 2 or more faults. Z is the number of meters of cloth before finding this one with 2 or more faults. So we're basically redoing parts B and C with this slight change in probability. Z now is following a geometric where it was previously, of course, a Poisson, and hence why I've kept the x, because that x was for our Poisson. And we've got our 0.1912. Okay, I want to know if he finds this before he has cut 3 1-meter lengths. So what's the probability he finds this in fewer than 3 attempts? That's the same as z less than or equal to 2. We've got a formula for that. That's 1 minus the probability of failure to the power of 2, which is 0.3458. Now, assuming those rolls of fabric are independent, then any given roll has a 0.3458 chance of having this particular issue, and then you're doing that twice, so 2 consecutive rolls. So we're just going to end up with 0.3458 squared, which gives us a chance of 0.1196. So something that can appear quite an overwhelming part of a question, if you take it through step by step and work your way through the question line by line, not anticipating getting to the final answer without having to dig some way into the question initially, it works itself out quite nicely.